Good afternoon, everybody. I want to welcome you to our statistics seminar. Today we're in for a real treat. We have Hossain from Nemours. He's the manager of Biomedical Statistics Core Research. He also has an adjunct appointment. Professor at the University of Delaware. Teaches graduate courses, undergraduate courses there in statistics. And today he's going to talk to us about piecewise linear mixed effects. And I'm actually quite excited to hear that because I'm actually doing a project where I'm doing piecewise.
Thank you very much. And good afternoon, everybody. Thank you for being here in this presentation. As our form says again, this is Hossain. I'm from the Nemours. And we will tell you here piecewise linear mixed effects model in tracking the mean response trend. And we will have an application with artists' childhood growth patterns. Here is the outline. Like we will first briefly describe the analysis of longitudinal data, then modeling the mean response, that is the primary goal, and then piecewise linear regressions. And for the longitudinal data, when we model the mean response, we need to specify the covariance among repeated measures. Then linear and piecewise linear mixed effects model, and at the end, we will see an application to the early childhood growth pattern. The primary goal of the longitudinal data analysis is to model the mean response over time, and their relationship to covariates, like other variables, other factors that can influence the response. But in the longitudinal setting, the repeated measures among the same individuals are correlated. And in the analysis of mean response, we need to consider that correlation. That's why classification of the covariance among repeated measures is also important for the longitudinal data analysis. There are two broad approaches for the analysis of the longitudinal data. One is just to analyze the response profile, and another way we can do, like express the response in terms of the as is longitudinal over the time, express the mean response as a function of the time. When repeated measures, I'm talking about the analysis of response profiles. What is that? Like when repeated measures are collected from at the same occasions or sequence of the same occasion for each individual, we can summarize the data. We can summarize the data like for each time points, and for each time points, and then like here we have. I guess I cannot use this one for the mouse. Not working very well. But anyway, like here the response profile, like when we collect the measures at the same occasions of time for each of the subjects, then we can summarize the data for each of the occasions and sequence of any measure of any group of the sequence of the measure for any group is called a response profile. The hypothesis concerning the response profiles is how the how the profiles are the or the how the are the mean response profiles similar across the groups. I mean, here we have two profiles. Are they similar? By similar we mean are they parallel? And that is the main concern of the hypothesis testing in the longitudinal data analysis. Not only for the response, but basically this is the same thing for the any longitudinal data analysis. Once we fail to detect the null hypothesis, that means if we have this, like that, if they are not parallel, that means like we need to go further analysis to see which of the variables or which of the groups are different and how it differs over the time. So we need to think about the post-analysis of the interaction. But if we fail to detect the null hypothesis, the first question will come, okay, is that how in each of the groups, how the profile changes over the time. Or the other way, we can say, like, are the means constant over time for each group. And then are another question we can ask, are the mean response profiles between groups at the same level? You can see here the response profiles are the parallel, but they are not at the same level. They have a gap, and a significant gap. The second approach of presenting the longitudinal data is the expressing the mean response as a parametric or sample parametric curves. When we express the patterns of the longitudinal data, the mean response of the longitudinal data comes for polynomial time. And here is some of them. We have you can see the polynomial how we are expressing when we expected yi means for the response for the ith subject, and we are expressing that as just as a function of the time. And of course, we can invoke many other variables. But the straight line in the curve, the simplest curve basically is the straight line, because rate of slope or the rate of change are constant and easy to interpret. The interpretation becomes difficult as the polynomial of degree of polynomial increases. For example, if you consider a quadratic polynomial, then it is like beta 1 plus beta 2. I mean, like that is a function of the time. That is a function of the time. And only thing we can do, like if you would like to know the changes, things, how it occurs, we need to consider the instantaneous rate of change at a particular time, and not very convenient. In many applications, actually, we observe irregular rates of changes and during the study period. Means by irregular rates of changes, we mean that changes occurs very quickly, like that. Fluctuates very quickly, like the very fast changes, then followed by slower changes, or increasing by decreasing. Nonlinear terms of this type may not be well approximated by polynomials of any order. One way to represent polynomial curves of this type is to have sequence of connected line segments that produce a piecewise linear curve. Means like you will divide the time axis into segments and fit the linear regression in each of the segments. That means you need to consider a model that accommodates all a linear form in each of the segments. places or the connecting point of the two segments, we call them node. Linear time models accumulate longitudinal data with theta relativity in terms of timing and number of measurements. Just think about the response profile. You have to have the collection from each subject at the same occasions of time, but this allows you a continuous or any sequence of measurement. For example, if you think about the EMR data or if you think of the BMIz data of the different sections, and this will not be, never be, the measurement it cannot have at the same sequence of occasion or same occasions. So we need to accommodate the unique sequence of measurements, and that's what actually we are aiming from the parametric or semi-parametric parts. Here is a growth curve, early childhood, the children who are like from birth to until 5 years, and here is how they are growing over the time in terms of their BMIz score. We will have that explanation in that, at the later. But this is the central scores of the BMI body-mass index, how it changes over the time. It looks like cubic polynomial, and of course we can come with this clinical, with this form of the polynomial form. But if we express piecewise, here is the piecewise linear form, and where beta k represents the changes in the rate from that is a prior segment. Means basically the beta associated with the splines actually represents the difference of the rate of change between two consecutive segments. So that was about the piecewise linear regressions. Now let's talk about a little bit about the covariance. There are three actually general approach or broad approaches for the covariance. The first is the unstructured covariance. That means you are not imposing any restriction on the covariance pattern. Just whatever it is, like Greek, you are calculating from the data and you are using exactly that's the covariance. But the problem is number of parameters. For this covariance pattern, we have to calculate if the number of timings n for the measurements, then we have the number of parameters we have to calculate n into n plus 1. N number of variables. The variable should be n numbers and the together variance and covariance parameters n into n plus 1 by 2. For example, if it is a two-time measurement, we will have three measurements, two variants, and another covariance. For the 3, it will be 3 times 4 by 2 in 6 parameters. So it grows very fast. And in statistical, modeling, one of the concepts towards parsimony of the model, we always try to avoid creating many parameters. So that is the problem of using the unstructured methods, but it brings the actual covariance pattern for the data. To avoid this situation, there are many models are proposed. Here are the some name compound symmetry, first order regressive, and clockwise exponential. The compound symmetry assumption is that the correlation is always constant among the repeated meters no matter what. It is not considering any time or the distance between the two measurements. And first order regressive, clockwise exponential, these are other methods. We cannot go, and this is not our goal actually, but just wanted to see what other methods here. Random effects covariance structure is another method. And in this method, repeated meters are expressed as a function of the random effects. Think about other model. There, covariance is just accounting for the within subject variation by introducing in a model the random effects and using random effects as a estimation of the, or for the modeling the covariance pattern. Basically you can use between subject variation also in the covariance pattern. For example, suppose you have a two groups and one is receiving like medication, one is receiving placebo. Basically within subject the covariance we may have changed that using random effects covariance structure. We have that flexibility. So the main thing we are on now, linear mixed effects model. We know that here is the model, like the expectation of yi, which would be xi beta. This one. So that is, we can use also longitudinal, that model we talked about before, like that in the previous slides. We can express longitudinal in that situation. And here, beta is our main interest, and beta is the population parameters or population characteristics. But the linear mixed effects model, actually, we can, like, it allows actually us a subset of the regression parameters to vary randomly from one individual to another individual. That's how we are accounting the subject level variability, and that's why we will see here what is the model for the population and what is the model for the subject level. And the good thing of the subject level analysis, you will have the heterogeneity of the subjects, each subject, and you can do many other data mining, like who are the subjects or who are the patients are getting better response than others. You can find it out. So many other things you can do based on this. And of course, model the linear mixed models actually also model the mean responses, as I said, as a combination of the population parameters. And you understand that when we say population mean, that is actually the response actually is contributing from every subject, all subjects. Then in the mixed model, in addition to this, we also add the subject specific mean changes, and that is unique to each individual. And as I said, that it also expresses the covariance and the repeatability as function of the time. I mean, like, if the time is our random effects, function of the random effects. General form of the, here is the general form of the longitudinal data, and this is for the Laird and Ward. They proposed this 1982, and I guess they brought a huge changes, evolution in the analysis of the longitudinal data with the introduction of the linear mixed effects. And of course, here yi is the response for the ith subject over the time. And our main interest is equal to beta and also the bi. In addition to for the covariance and those things, we need to know like the distribution, or we need to estimate the parameter like the residual. Our assumption is residual is distributed as normal, multivariate normal with 0, and covariance pattern Ri, and subject specific effects Bi is distributed with normal also with mean 0 and a covariance pattern G, matrix G. So we need to know all of them. Here you see some of them is I, some of them is like constant no I. When we do not see I on that, that means it is not varying from the subject to subject. And for the subject level, when we say the D is a confirmatory metric, that means we are considering the subjects are coming from the same population, so the subject level distribution for the variation, the covariance matrix we put as a same for it. So as I say here, the first, this one is the response profile. See, this is the, still we are talking about the mean response, but conditioning on the subject level effects. These PI are subject level. And this part basically population characteristic, and this part is the subject changes from the population characteristic. And then together we have the subject level profiles. And when you take the mean of this one, you are getting actually the population. So population parameter, yeah, mean, the marginal mean is still the average of the subject level means. And one more thing we need to know, the distribution of this yi means the response, and bi the subject specific effects, and they are normal, and here is the covariance matrix. That's what we need, because ultimately we will estimate the bi of subject specific effects using the concept of this normal distribution. And we know from the normal distribution, before that, this is the beta. We need to estimate the population parameter, that is beta. Only things we need to know. And then for the precision level of our estimate, we need to know the covariance of the estimate. When we think about the subject level, then effect, then basically we need to estimate the BI, that's the subject specific effects. And we are estimating actually this one. A mouse is, yeah, mouse is really very hard to work with. So, subject specific effects, as we know, conditional, like, think about a two multivariate normal variables. Like, we know if two of the, like the multivariate normal, we can easily calculate the conditional mean of that one. Like the suppose y1 and y2, two are two multivariate normals, and the expected value of the y1 given y2 is a function of y1, and that is in a statistical sense, that is a linear unbiased estimator. And that's what we like, or the linear unbiased prediction, actually, not estimator, because that is the function and then a variable. So that is linear unbiased prediction. So that's what we use. See, expected value of bi given yi. Bi and yi both are normal, multivariate normal, and we saw there. It was fine now. And see here the covariance matrix, and here is the mean, and utilizing this, we know how to calculate. And here is the theory. You can see here, these are the multivariate normal distribution, and expected value of the y1 given y2 is this, and the variance covariance matrix is this. Utilizing the concept, we can estimate bi, and that is the best linear unbiased predictor. Think about the beta estimate population, and this is the bi estimate. That's what we need to estimate. And once we have the estimation, that means we are done with what we need from the model. And then piecewise, for the piecewise, we are not doing anything else except the introduction, the concept of the piecewise linear things in the matrix of Xi and Gi. The Xi is the population. The design matrix means design matrix for the population, and Gi is the design matrix for the for the random effects. And basically, more often, actually, most of the time, Gi is the subject of the Xi. But of course, it can. You do not need to follow all the same rule, but usually people keep as a subset. So this is now we are introducing the spline in the random in the Xi and Gi, and that's how we have this model. I don't know what this I stand for. You know, all of them got like what is these things? But this is the model. Oh, that is plus actually. Beta 0 plus, beta 1 Tij plus, beta 2 Tij minus T1. I guess like we are missing some of the plus and minus things from the slides. So not missing, basically it's not coming up. But the whole idea is again the beta estimate and the BIs. All those BIs, that is subjective specific pairs, and beta are the populations parameters. So we will see an application of this concept to the growth pattern. Think about your kids, my kids, and a cohort of the kids. How do they grow? Their growth is not like completely heterogeneous. Unlike that, someone is growing, so many things actually affecting, like the genetics, environment, good behaviors, so many things, and also comorbidities. So we have 3,365 patients. We'll see how the child grow in terms of their weight gain. When I say weight gain, or both like that, I mean weight gain in terms of the gain in height. So for that, like that's what it is, physical growth, we believe, right? And for the physical growth, weight to length and body mass index are two commonly used indices. Weight to length is an average weight for a given height, and body mass index is a weight given by height square when it is measured in kg and meter. Standardized scores of these are like weight to length score and BMIz score, and we name both as BMIz. But remember, for the children less than 2 years age, we are talking about the weight for length, and after that BMI. But we are able to merge both the data because in the G score they are the same variable representing, and actually all the cutoff points also are the same. And this is when we say this word, that is, we are saying that standardized normal variables. So you understand that in an ideal situation, we'll expect -1 to 1. What percentage of the population? 68. And from minus 2 to 2, how many? 95. And minus 3 to 3, 99.79. So basically, by minus 3 to 3, basically we expect whole population, more or less. The reason I'm saying this, we will see the rate of change, yearly rate of change, even point something. Even point something is a very big change in terms of the measurement, like -1 to 1, -2 to 2. Of course, the study population is the children aged 0 to 5, and we see how they grow for the time. Inclusion criteria was they have to have the first visit at Nemours, any Nemours clinic by less than 1 month of age. And exclusion criteria was, at least one visit thereafter for each year. We put this restriction to make sure that we have enough number of measurements to include for our, or to talk about their trajectories. Exclusion criteria is medical conditions of growth, such as cancer and cystic fibrosis. As I said, we are talking about 3,365 children. Data were collected on their training visits and detailed from Nemours Biomedical Record. So, you know the data. We are talking about we have the height, weight, and all other information on their clinic visits. And we are using that. Anyone understand that each patient's clinic visits are different from others? Basically, we are working with the 3,361 patient sequences, different sequences. It will never match. The linear mixed model is accommodated all those kinds of features. And one more thing we did here, BMIz, I interpolated at the age of 1 and at the age of 60 months, because we cannot expect actually like everybody will be present at their 60th month. What we did, like on the 4th and 5th, right after the 5th birthday, when they have the measurement, we interpolated one of them like that at the 60th month. And in the other reason is like another reason of like the interpolating at the age of 1 month. Many subjects actually had many visits, more than, like some of them have had 4 visits, 5 visits at the very beginning, like the first week, second week, like that. And then the problem is so many, I did not want to put so many of them like in the measurement, in the analysis to avoid, like think about like the very small kids. If you, when you measure them, height and weight, a minimum, a small change brings a huge mistake on that, or huge changes in the G-score. Like height and weight, they are very sensitive that time. So I just want to restrict at like less than 1 month, just measurement as a interpolation of one measure at that point. Well, we have about 49% male and 51% female, and of course 43% Caucasian, 45% or 46% African American. The region is like we have many, so it's not well represented the whole USA population, because like we have by race and ethnicity, you can see Caucasian is 43% and African American is 46%. The reason we have like many African American patients in the Wilmington, we have some clinics in that area and Philadelphia area, so we have a over-representation of African American. But we have enough subjects to take a look of their own, in their own group, the growth patterns. Here is again the same one. Now you know that this is the BMIz score. That is the standardized scores of the weight per day and the BMI. And how do we go about that kind? Analysis shows like 8 and 22 months, the norms at 8 and 22 months is the best results or the best model for me, and that's what I accepted as a norms for the feed the growth trend in 3 different segments. Again, the model is here, the same model we talked. Like we have the population changes. We are modeling actually mean changes, means expectation of YIZ. The YIZ represents the BMIz, and we are actually we are actually modeling the mean change in BMIz, condition on the subject level, heterogeneity, and like how we condition these few things like the timing, adding the time over the time. That means we are extracting the growth pattern of each of the subjects over the time. So let's take a look at how do they grow. As I have, one more thing, like we do not have the birth weight for the each subject because like we do not have the maternity. Basically, children comes to educate us after their birth. So we do not have maternity information much. And here, as I said, I interpolated at the age of month 1, and we have the data until the 60th month. Here is the first one, mean BMIz at the estimate of the mean BMIz at the age of 1 month. By significant here, I mean it is significant different from 0. The ideal situation. That's what our expectation. Like it is a standardized normal, and the median or mean, everything belongs to like that. Everything should be 0. So yeah, this is like the little higher at the beginning of 1 month. Then we have so far we have 3 segments, like 1 to 8 months, 8 to 20 months, and 20 to 60 months. We will see in those areas, in those segments of the time, how do they grow. Here is the like rate of change is 0.15. That means per year, according to the rate of change, it is 0.15 for the, if we say per year, in terms of the year, but it is 1 to 8 months. And when I use the data, basically we calculate the estimate as a per year change. So this is the 0.15, and of course very significantly, because our change, a small change, is also very high, because like our data belongs to -2 to -3 to 3. So 0.15 is a very big changes, and that's what we see. Yeah. In the second segment, you see like it goes down. The changes in the BMIz goes down. So it goes up and then goes down, and again goes up. So here you can see it heavily goes down in the from 8 to 22 months. That means weight gain in terms of the growth pattern. Think about the BMIz, what it represents, weight in terms of the height. So the way we have the measurement now, in terms of that, the gaining weight is less in this period in terms of their weight. So growth pattern, like in this area, they are actually -10. And here, rate of change again, again, the weight, they start gaining their weight after 2 years. So here you see fixed and random. When we talk about the population parameter, or when we talk about how the overall population grows, that's what we saw. The thing is that, like, we have individual prediction also. We have like all the coefficients, all these coefficients for each of the subject. We cannot express all of them together. We cannot bring the growth of all the subjects here. One thing we can do, summarizing. Like the first thing we need to look at how the growth pattern among the individual to individual vary. So that is coming from the variance of the BI estimates. that variance of the subject level effect. You can see in each of them had the huge variability. It simply says, even though we are talking about the population, either increase or decrease, whatever it is, that's the things we are talking, right? But still, when we talk about the population, but still, not all of them are following the same trend. They have a huge variability, like individual to individual. And that's what we have here. And all of the parameters we see variable. This one simply says, like, even at the 1 month, their mean BMIz is significantly different from each individual to individual. That is true. Someone is, even when they are born, still it is different. And then here, like how do they grow in the past? Yeah, in the past segments, and you can see the very significant variability between subjects. So that means the trend we are talking for the population, not everybody follows the same things. Even we say the population, like the increasing trend, some of them even have the decreasing trend, and that's what we will see even at the later. What is the percentage of the population is decreasing and increasing? So see, in the past segment of time, we have 55% of the population like gaining weight, like that in terms of the BMIz, they are increasing. They have an increasing trend of the BMIz. When they have like the increasing, and 45% definitely have the decreasing trend. So it is like a population, as we are talking about the average. That is, even though we see a scenario for the population, it's not always the true for the subject level. And then in the second part, we saw a huge decreasing trend in the population, and that is almost 67% of the children has a decreasing trend, and 33 have a increasing trend. And then the last part, we have 70% of the patient, or not 70% of the individuals or children have an increasing trend in BMIz. When I say BMIz, that is, you know that body mass index and weight for that. Here is the Lewis curve for the male and female. The male is top, the bottom is the female, and of course their growth pattern is over the time significant. Their interaction is, like, if you think about the interaction of gender and time, and that is very significant. And here at the beginning of the life, your male are have a little higher growth or higher increasing compared to the female. And after the 2 years or 2.5 years, you can see like they are in the same trend. Yeah, very close. That means at some point of time, the girls starting gaining their weight too. And here we can see how individual level and how the girls and boys grow. You can see here the male and female, and here is a, like at the beginning, the 0.34 and 0.36. That means at 1 month, male and female has a more or less average same mean. And then you see slope, like the change in the first segment of the timing is much lower than male. And that's what we saw. Like the curve was very high for the male. And then here, like in the second segment, both male and female decreasing losing their weight in the same trend. And then again, in the third segment, male increasing, female increasing in a higher rate, and female growing, getting the weight in a higher rate compared to the male. And as we have a huge number of subjects, all those changes are very significant difference. And here you can see 53% of the female gain weight in the first segment, while 58% of the male gain weight in the first segment. And in the second segment, their growth and their gaining weight is the same, about 33%. But in the third segment of timing, we have 73% children, female children, have an increasing trend, while we have a decrease, only 66% in the male. That means, like, this is the percentage gaining weight, and you see, like here, like if it is 67% gain weight, you know what percent are not gaining weight, like 33, right? So see, like that's what we see. More children, more male children is growing, gaining weight, very rapid weight gain after about 2 years timing. Female and male children getting higher weight at the beginning of the life. Here is the race. Although I said it's smooth, it is not that much smooth. Of course, for making low edge smoother, all you need to make the window bigger. But as you go for the low window, smoother, you are losing you are trading with the precision. So I just wanted to keep it like not too much smooth or not. I mean here, even though I say it's smooth, but it is not that smooth. But I don't want to lose much precision to get more smoother. And here again, see, here is the Hispanic. They grow. They are born at their beginning of their life with a higher weight, and they maintain the level of the weight. At that level difference, the level of the difference they maintain over the time. And here is the black one is Caucasian, the red one is African American. You will be surprised that these higher also like the high things at the beginning of the life, like the African American in the first segment has a significantly higher increasing rate. Unlike the increasing rate means increasing the BMIz compared to the Caucasian. And they are pretty, here African American is a little flatter than the Caucasian. They go directly down, and then again Caucasian is getting up, and they are actually pretty close. Again, we have the measurement here, everything, how they grow, Caucasian children and African American children. And here you see here, at the very beginning, African American had a high BMIz, mean BMIz is 0.4, and while Caucasian has a 0.22 mean BMIz. And then in the first segment, the Caucasian have a higher rate of change compared to the African American, higher rate of increase compared to the African American, and that's what we saw. Like And then as like that at the beginning of their, they have a little high weight and they goes down quickly, and here they go up. And that's what we saw here. Even at the beginning they are going up, and then here is little up, and then basically quick down. And in the second slope, they have a, like the Caucasian has a lower rate of decreasing. That's what we see. Even 33% is gaining, while here 31% gaining. And again, how do they increase in the population level? Like 12.12 and 0.14 increasing rate. That means at this level, like in the third segment. So at the beginning, Caucasian has a higher increase, gaining, and then compared to the African American, and then at the second slope, they are pretty not same, but it's closer than other segments. And then here, like in the third segment, they are 11.9. Yeah, like they are also pretty close, but African American has a higher rate. And you can see here 68% and 70% children in the third segment, means after 2 years of timing, the 68% Caucasian children gain the weight, and while African Americans 70% gain the weight. So that's what my goal was to present. Now you can know what is the conclusion asked about the feasibility of the piecewise linear mixed sequence model, what it does in the response profile. Many of us, we do that is like the analysis of response profiles actually using the repeated measures. And basically, if we have measurement time times like the grouping, that means in the cell, we are putting the cell mean, and almost we are trying to fit a saturated model. Here, we are saving some of the parameters, and also we have the feasibility. You can have a sequence of unique sequence of measurement for each individual, and you can have any number of measurements, and also like the covariance also you can express also in the repeated measures, like that as a function of the random effects. The good thing of that, it again allows you it means it does not depend on the number of timing or number of measurements. In the response profile, suppose you have a 5 time measurements, that means 5 times 6, that means you are measuring 15 measurements, 15 of them. But here, if the model, if the 10 only depends on the form of the 10, if it is like linear, you are measuring 2 of them, beta 0 and beta 1. Actually, that is you regress, in the covariance, or the covariance pattern also, B0 and B1. That is as a random effect. And variance and covariance matrix of that is that will give you 3 parameters. But if you have like quadratic, you are setting, if you set piecewise, that means intersect and 2 slopes for 2 segments, that will give you 3, and you can add any number of measurements, any number of measurements. And this is the feasibility of the piecewise linear mixed sequence model. And as we talk about the population application, the growth pattern is like a cubic polynomial over the time from 0 to 5 years. And children, like male and female, has a completely different growth pattern. Not complete, I mean like that. Maybe not like that in the form, but in the shape. They are different, and also like we have some differences based on the African race and ethnicity. In fact, I found more like the race and ethnicity is like by gender, like the African American, and male and female has a less difference than Caucasian male and female. But anyway, that was my presentation about, and please let me know if you have any questions. And I'm done with the presentation.